Section 10.6 is about maximum differential entropy distributions. Before we discuss Section 10.6, we first discussed Section 2.9 on maximum entropy distributions, which is the discrete version of Section 10.6. We have deliberately deferred the discussion of Section 2.9 until now. Consider the following maximization problem. Maximize the entropy H of P, where P is a probability distribution defined on a countable subset S of the set of real numbers. The idea is illustrated in the figure. So what it means is that it is not necessary for P to be defined for all real numbers. Rather, we only need to define P on a countable subset S of the set of real numbers. We impose the constraints summation x in the support of P, Px times Ri of x is equal to Ai, where I is from 1 up to m. That is, there are a total of m such constraints on the distribution P. Whereas P is the support of P, which is a subset of S, and Ri is a function defined for all x in S. Note that the summation in equation 1 is simply the expectation of the random variable Ri of x with respect to the distribution P. The most important theorem in this section is theorem 2.50, which gives the form of the P that maximizes the entropy subject to the constraints. Let P star of x equals e to the power minus lambda 0 minus summation I from 1 up to m, lambda I times Ri of x. For all x in S, where lambda 0, lambda 1 up to lambda m are chosen such that the constraints in 1 are satisfied. Then P star maximizes H of P over all probability distribution P on S subject to the constraints in 1. Note that P star of x, because of the exponential form, is always strictly positive, and so the support of P star is equal to S. If we let Qi equals e to the power minus lambda I, then we can write P star of x equals e to the power minus lambda 0 e to the power minus lambda 1 times R1 of x all the way to e to the power minus lambda m times Rm of x, which is equal to Q0 times Q1 to the power R1 of x all the way to Qm to the power Rm of x. From this form, it is clear that Q0, that is e to the power minus lambda 0, is the normalization constant because P star of x summing over all x must be equal to 1. We now give the sketch of the proof of theorem 2.50. For the sake of convenience, we are going to use the natural logarithm. Consider entropy of P star minus entropy of P, where P is any distribution on S that satisfies the constraints in 1. This is equal to minus summation x in S, P star of x log P star of x, plus summation x in SP, P of x log P of x. We are going to justify that we can replace P star of x in red by P of x in blue, and the summation over x in S, where S is in red, by summation over all x in SP, where SP is in blue. Combining these two summations, we have summation x in SP, Px log Px divided by P star x. This is equal to the divergence between P and P star, which is greater than or equal to 0. This shows that P star is the distribution that maximizes the entropy. We now fill in the details of the proof. First, entropy of P star minus entropy of P is equal to this, as we have seen. Now P star of x is equal to e to the power minus lambda 0 minus summation I lambda I Ri of x. And so the natural logarithm of P star of x is equal to minus lambda 0 minus summation I lambda I Ri of x. So we substitute this expression for log p star of x. Now we are going to split the first summation into two. First, we have lambda 0 multiplied by summation x in S p star of x. And for the second summation, which is a double summation, we first sum over summation I, lambda I, and then summation x in S p star of x multiplied by Ri of x. Now summation p star of x over all x in S is just equal to 1. And summation x in S p star of x Ri of x is equal to ai, because lambda 0, lambda 1 up to lambda m are chosen such that p star satisfies all the constraints in equation 1. Now for this one, we replace it by summation px over all x in SP. And for this ai, we replace it by summation px times Ri of x over all x in SP, because p satisfies all the m constraints in equation 1. Note that we have already replaced p star of x in red by p of x in blue, and S in red by SP in blue. In the remaining, we just inverse the operations in the second and the third steps of the proof. To recombine the first two summations into one, we first sum over x in SP, p of x. With this minus sign in place, we have minus lambda 0 minus summation I lambda I times Ri of x. Now minus lambda 0 minus summation I lambda I times Ri of x is equal to the natural logarithm of p star of x. And so we have summation x in SP, px log px divided by p star of x, which is the divergence between p and p star, and this is greater than or equal to 0. This completes the proof of the theorem. Theorem 2.50 has the following rather subtle corollary. Let p star be the probability distribution defined on S that we have seen before, except that lambda 0, lambda 1 up to lambda m are now arbitrary constants. Then p star maximizes the entropy of p over all probability distribution p defined on S, subject to the constraints summation x in SP, p of x times Ri of x is equal to summation x in S, p star of x times Ri of x for all I between 1 and m. The proof goes as follows. Let summation x in S, p star of x times Ri of x be ai for all I. Then by construction, the parameters lambda 0, lambda 1 up to lambda m in p star of x are such that p star satisfies the constraints summation x in SP, p of x times Ri of x is equal to ai for all I. Then the corollary is implied by theorem 2.50. Example 2.52 is an illustration of an application of theorem 2.50. Let S be finite and let the set of constraints be empty. Then p star of x is equal to e to the power minus lambda 0, which does not depend on x. Therefore, p star is simply the uniform distribution over S. That is, p star of x is equal to the reciprocal of the size of S for all x in S. This is consistent with our previous result that over a finite alphabet, the entropy is maximized by the uniform distribution. The next example is a little bit more elaborate. Let S be the set of integers 0, 1, 2, so on and so forth, and let the set of constraints be summation x px times x equals a, where a is greater than or equal to 0. That is, the mean of the distribution is fixed to be a. Let qi equals e to the power minus lambda I for I equals 0 and 1. Then p star of x is equal to e to the power minus lambda 0 times e to the power minus lambda 1 times x, which is equal to q0 times q1 to the power x. Evidently, p star is a geometric distribution, so that q1 is equal to 1 minus q0, where q0 is the normalizing constant. Thus, it remains to determine q0. Toward this end, we invoke the constraint in equation 1 on p to obtain q0 equals the reciprocal of a plus 1. This is the only choice for q0 to make the mean of the distribution equal to a. Let us now return to section 10.6 on maximum differential entropy distributions. Consider the maximization problem. Maximize the differential entropy over all probability density function f defined on a subset S of the nth dimensional Euclidean space. Subject to the constraints, integrating Ri of x f of x dx over the support of f equals ai for all I from 1 up to m, where the support of f is a subset of S and Ri of x is some function defined for all x in S. Note that the integral in equation 1 is simply the expectation of the random variable Ri of x with respect to the distribution f. Theorem 10.41 is the continuous version of Theorem 2.50. It says that the differential entropy is maximized by f star of x, which has the form e to the power minus lambda 0 minus summation I equals 1 up to m lambda I times Ri of x, where lambda 0, lambda 1 up to lambda m are chosen such that the constraints in equation 1 are satisfied. Theorem 10.41 has the following corollary. Let f star be a PDF defined on S, with f star of x being the same as we have seen before, where lambda 0, lambda 1 up to lambda m are arbitrary constants. Then f star maximizes the differential entropy over all density function f defined on S, subject to the constraints, integrating Ri of x fx dx over the support of f is equal to integrating Ri of x f star of x dx over the support S for all I from 1 up to m. Theorem 10.43 says the following. Let x be a continuous random variable with the second moment being kappa. Then the differential entropy of x is upper bounded by 1/2 log 2 pi e kappa, with equality if and only if x is a Gaussian random variable with mean 0 and variance kappa. The proof goes as follows. We consider maximizing the differential entropy of f subject to the constraint, integrating x squared fx dx, that is, the expectation of x squared, equals kappa. Then by theorem 10.41, f star of x has the form a times e to the power minus bx squared, which is the Gaussian distribution with zero mean. In order to satisfy the second moment constraint, the only choices are a equals 1 over square root 2 pi kappa and b equals 1 over 2 kappa. Next, we are going to illustrate an application of corollary 10.42. We start with the PDF of a Gaussian random variable with mean 0 and variance sigma square, and call this density function f star of x, which is equal to 1 over square root 2 pi sigma square e to the power minus x squared over 2 sigma square. We ask what are the constraints that F star maximizes the entropy for. To answer this question, we write F star of x equals e to the power minus lambda 0 times e to the power minus lambda 1 times x squared, where lambda 0 is equal to 1/2 log 2 pi sigma square, and lambda 1 is equal to 1/2 sigma square. Then, according to corollary 10.42, F star maximizes the differential entropy over all density functions subject to the second moment equal to sigma square. The next theorem says that for a continuous random variable with mean mu and variance sigma square, the differential entropy is upper bounded by 1/2 log 2 pi e sigma square, with equality if and only if x is a Gaussian random variable with mean mu and variance sigma square. The proof goes as follows. Let x prime equals x minus mu. Then x prime has 0 mean, and the second moment of x prime is equal to the expectation of the square of x minus mu, which is equal to the variance of x, that is sigma square. Then by theorem 10.14, that is the translation property, x and x prime have the same differential entropy, and then by theorem 10.43, the differential entropy of x prime is less than or equal to 1/2 log 2 pi e sigma square, because the second moment of x prime is equal to sigma square. Equality holds if and only if x prime is the Gaussian random variable with mean 0 and variance sigma square, or x is the Gaussian random variable with mean mu and variance sigma square. The following remark is somewhat subtle. Theorem 10.43 says that with the constraints that the second moment is equal to kappa, the differential entropy is maximized by the Gaussian distribution with mean 0 and variance kappa. If we impose the additional constraint that the mean is equal to 0, then both the variance of x and the second moment of x are equal to kappa. By theorem 10.44, the differential entropy is still maximized by the Gaussian distribution with 0 mean and variance kappa. Now we discuss a relation between differential entropy and the spread of the distribution. From theorem 10.44, we have the differential entropy of a random variable x is less than or equal to 1/2 log 2 pi e sigma square, where sigma square is equal to the variance of x. This upper bound can be written as log sigma plus 1/2 log 2 pi e. Then from this inequality, we see that the differential entropy is at most equal to the logarithm of the standard deviation, which is a measure of the spread of the distribution, plus a constant, that is 1/2 log 2 pi e. In particular, as sigma, the standard deviation, tends to 0, the differential entropy tends to minus infinity. The next two theorems are the vector generalizations of theorem 10.43 and 10.44 respectively. Let x be a vector of n continuous random variables with correlation matrix K tilde. Then the differential entropy of x is upper bounded by 1/2 log 2 pi e to the power n times the determinant of the correlation matrix K tilde, with equality if and only if x is a Gaussian vector with mean 0 and covariance matrix K tilde. Theorem 10.46 says that for a random vector with mean mu and covariance matrix K, the differential entropy is upper bounded by 1/2 log 2 pi e to the power n times the determinant of K, with equality if and only if x is a Gaussian vector with mean mu and covariance matrix K. We now prove theorem 10.45. Define the function Rij of x to be xi times xj, and let the ijth element of the matrix K tilde be K tilde ij. Then the constraints on the PDF of the random vector x, namely the requirements that the correlation matrix is equal to K tilde, are equivalent to setting the integral of Rij of x fx dx over the support of f to K tilde ij. It is because Rij of x is equal to xi times xj, and so this integral is equal to the expectation of xi times xj. That is the correlation between xi and xj, and this is for all ij between 1 and n. Now by theorem 10.41, the joint PDF that maximizes the differential entropy has the form f star of x equals e to the power minus lambda 0 minus summation over all I and j, lambda ij xi times xj, where xi times xj is Rij of x. Here, the summation over all ij, lambda ij times xi times xj, can be written as x transpose L times x, where L is an n by n matrix with the ijth element equal to lambda ij. Thus, f star is the joint PDF of a multivariate Gaussian distribution with zero mean. To see this, we only need to compare the form of f star of x and the PDF of a Gaussian distribution with mean 0. Then, for all ij between 1 and n, the covariance between xi and xj is equal to expectation of xi times xj minus the expectation of xi times the expectation of xj, where the expectation of xi is equal to 0 and the expectation of xj is also equal to 0. And so, we have the covariance between xi and xj equals the expectation of xi times xj. Hence, the covariance matrix corresponding to the PDF f star is equal to K tilde because the expectation of xi times xj has been set to K tilde ij. Now f star is the joint PDF of a multivariate Gaussian distribution with zero mean, and the covariance matrix is equal to K tilde. Accordingly, lambda 0 and L in f star of x have the unique solution given by e to the power minus lambda 0 equals 1 over square root 2 pi to the power n times the square root of the determinant of K tilde. And L is equal to 1/2 the inverse of K tilde. So that f star of x is equal to 1 over square root 2 pi to the power n times the square root of the determinant of K tilde times e to the power minus 1/2 x transpose times the inverse of K tilde times x, which is the joint PDF of the Gaussian distribution with mean 0 and variance matrix K tilde. Hence, by theorem 10.20, which gives the differential entropy of a Gaussian distribution, we have proved the upper bound on the differential entropy of the random vector x in terms of the correlation matrix K tilde, with equality if and only if x is a Gaussian vector with mean 0 and covariance matrix K tilde.